Hello everyone. This is the video lecture series of solid state devices. Course code EC301, contact hours 3 per week, credit 3. Myself, Dr. Shunipa Roy, Assistant Professor of Electronics and Communication Engineering Department of Guru Nanak Institute of Technology. This is Module 1, Charge Carriers in Semiconductor. This lecture is 24 number lecture. So module 1 describes all these things that is mentioned here. These are the prerequisites: conductor, semiconductor, insulator, knowledge, electrical properties, P-type, N-type semiconductors, different types of transistor configuration, the properties of transistor, working principle of field effect transistor, so these are the course outcomes. As per NBA guideline, we have 4 outcomes associated with this subject: CO1, CO2, CO3, CO4. There are different points mentioned in CO1, CO2, CO3, and CO4. This is the lesson plan of this lecture: intrinsic and extrinsic semiconductor, effect of temperature and energy gap of intrinsic concentration, effect of temperature on intrinsic semiconductor, deviation of equilibrium electron and hole concentration in terms of effective density of states and intrinsic level, derivation of electron and hole concentration in a compensated semiconductor. So what is semiconductor? Semiconductors are material whose electronic properties are intermediate between those of metals and insulators. So it has the conductivity of that lies between metal and the semiconductor. The interesting feature of semiconductor is that they are bipolar and current is transported by 2 charge carriers, that is electrons and holes of opposite sign. The intermediate properties are determined by actually the crystal structure bonding characteristics. So silicon and germanium are elemental semiconductors, all of you know, and they have 4 valence electrons which are distributed among the outermost S and P orbitals. The outermost S and P orbitals of semiconductors involved in sp3 hybridization. And this sp3 hybridization, these sp3 orbitals form 4 valence covalent bonds of equal angular separation, leading to the tetrahedral arrangement of atoms in space results tetrahedron shape. So let us come to the different type of semiconductor, that is intrinsic semiconductor and extrinsic semiconductor. Intrinsic semiconductor is nothing but the pure form of semiconductor, and extrinsic semiconductor is impurity added semiconductor. So what is intrinsic semiconductor? Intrinsic semiconductor is nothing but a pristine semiconductor. That is, it behaves as an insulator at 0 degree Kelvin and behaves as a conductor at higher temperature, is known as intrinsic semiconductor. This is very pure semiconductor. Germanium and silicon are the best example of intrinsic semiconductor, and they possess diamond cubic crystalline structure. Among germanium and silicon, silicon is mostly used because of availability in nature, and also the energy band gap is higher. As the energy band gap is higher, there is less possibility of minor leakage current. because at room temperature there is less possibility that valence band electrons jump conduction band electrons. Therefore, there is less possibility of leakage current. So this is the schematic of intrinsic semiconductor. 5 atoms, silicon atoms are there, and this middle one silicon atom is making covalent bond with other four, and this is covalent bond, and this is the valence shell. So this is just recapitulation that this is the conduction band denoted by EC, and this is green one, this is the valence band denoted by EV, and in between valence band and conduction band, this band gap is called forbidden energy gap. Why this is forbidden? Because no free electrons can be made available in this region. And one more level is showing, that is Fermi energy level. For intrinsic semiconductor, it is the midway of forbidden energy gap. And x-axis is showing the distance and y-axis showing electron energy. And this is the energy band diagram of intrinsic semiconductor. So here we can see that kinetic energy of hole is nothing but the EV minus E. This is the kinetic energy of hole. And the kinetic energy of electron is nothing but the E minus EC. So this much amount of energy is required to jump electron from this conduction band EC to extreme level of conduction band. So carrier concentration in intrinsic semiconductor. When a suitable form of energy is supplied to the intrinsic semiconductor, then electrons take transition from valence band to conduction band. It is obvious. Hence, a free electron in the conduction band and simultaneously free holes in the valence band is generated. And this phenomena is known as electron-hole pair generation. An intrinsic semiconductor, the number of conduction band electron is obviously equal to the number of valence band holes. So this is the very important topic, that is density of states. So what is density of states? Density of states is nothing but the available energy states per unit volume and per unit energy range. I repeat, density of states is nothing but the available energy states per unit energy volume per unit energy range. So if we draw you can understand better. This is a three-dimensional quantum wave. This is discrete energy levels. These are discrete energy levels. This is not to scale, obviously. Say the energy level, this is E, lowermost. And this is E plus del E. Now, if we consider this range, then obviously this range is nothing but the E plus del E minus E, that is del E range. This del E range has been presented, has been shown here. So the range is DE or del E, and if we consider this energy level is 0.5 electron volt and this energy level is 1.5 electron volt, then the energy gap is 1.5 minus 0.5, that is 1 electron volt. So within this energy gap, how many energy states are there? 1, 2, 3. So 3 energy states are there in 1 electron volt energy gap. So the density of state is 3. Hope now everybody has understood. Everybody has understood this one. So density of states is nothing but this one, Z of E into dE. This parameter is called density of states. That is available energy states per unit volume per unit energy range. So this density of states multiplied by the Fermi energy level or Fermi probability distribution function, Fermi energy distribution function, then this will give us the density of charge carriers in the conduction band. So if we integrate this function and put the limit of EC, that is entire conduction band range, then we are getting the total number of electrons in the conduction band, that is integration, putting the limit EC, Z of E, FE, DE. So Z of E, DE is the density of states, Fe is the Fermi energy distribution function, N is the total number of electrons available in the conduction band, whereas Dn was the density of electron available in the conduction band. So by putting the limit, we are getting the total number of electrons available in the conduction band. So this is the density of states, and the density of states can be denoted by, if we go to our next slide, it will be clear to us that density of states can be denoted by, this is the electron and hole density of states. That is, the density of electrons and holes are related to the density of states function and the Fermi distribution function. This Fe is the Fermi distribution function. This Ge is nothing but the density of states function, and the density of electron in the conduction band is N of E. Similarly, density of holes in the valence band is Pe equals to GVE 1 minus Fe. That is total probability, Fermi probability function, Fermi distribution function is Fe. So if conduction for conduction electron, if this is Fe, but therefore for electron probability distribution function, this should be 1 minus Fe. This is shown here. So total concentration electron and hole per unit volume is found by integrating the corresponding function over the entire conduction and valence band energy. We need to determine the Fermi energy in order to find the thermal equilibrium electron and hole concentration. So in case of intrinsic semiconductor at T equals to 0 degree Kelvin, all energy states in the valence band are filled with electrons and all energy states in the conduction band are empty. The Fermi energy must be somewhere between EC and EV. At T is greater than 0 degree K, number of electrons in the conduction band is equal to the number of holes in the valence band in case of intrinsic semiconductor. So before moving to our density of states function and its formula, let us discuss what is effective mass. So movement of an electron in crystal lattice is different from that of free space. So in addition to an externally applied force, there are internal forces in the crystal due to positively charged ions or protons and negatively charged electrons, which will influence the motion of electron in the lattice. So we can write F total equals to F external plus F internal. That is equals to force. Force is nothing but the mass into acceleration, we know, where F total is the total force, F external is the external force, F internal is the internal force. Now, as there are so many forces, internal forces are available and it is not possible to calculate these internal forces, then we can neglect this internal force. Rather, we can consider this external force that is Fx, and the formula can be modified in this way, that F external equals to M star A, not Ma. So what is M star? M star is the mass that has been affected by the internal force. That's why this is called effective mass. M star is effective mass. So moving to the next slide, this equilibrium distribution of holes and electrons is showing here. This is the density of state of electrons in the conduction band. This is showing the graph, and the formula is 4 pi 2 m star, that is effective mass of electron in the conduction band, and h cube, that is Planck's constant, to the power 3 by 2 into root over of E minus EC. This is the formula of density of states of electrons in the conduction band. Similarly, this is the formula of densities of states of valence holes in the valence band. So this is density of states of electrons in conduction band, this graph, and this graph showing density of states of holes in valence band, and this is the distributed function is nothing but the Fermi probability, Fermi distribution function, and this region, that is this cross-sectional region, this corresponds to this region. This is area of concentration N naught, and this is denoted by GE FEE, that is equals to NE. This is actually the total number of charge carriers present in the conduction band. Shaded region is showing, and this region is showing total number of holes present in the valence band. So if Mn star equals to Mp star, that is effective mass of electron is equal to the effective mass of hole, the Fermi energy is at the mid gap energy, and if these two effective masses are not same, the Fermi level for an intrinsic semiconductor will slightly shift away from the mid gap energy. So moving to our next slide, this is the N naught and P naught equation. So N naught can be written as the total number of electron concentration in the conduction band, as limit has been provided here. Already mentioned in earlier slide, all the nomenclature already mentioned. So N naught can be the limit of total function can be put here as EC to the infinity, because how long the conduction band is extended we don't know. That's why we have put here infinity, the maximum limit, and according to the Fermi-Dirac distribution function, this is the Fermi-Dirac distribution function. If EC minus EF is very, very greater than KT, that means maximum number of levels are occupied. Therefore, we can ignore this a to the power E minus EF by kappa T can be considered only, and this has been considered here in this equation. Now N naught we can put that this formula is nothing but the formula of density of states And this is, we have got the Fermi distribution function can be approximated in this way. Now this is E minus EC by kappa T, or minus E minus EF by kappa T, whatever. That is, we denote as eta, and this is a constant, and this constant is called ideality factor. And if we move to our next slide, we will find that this formula already mentioned in earlier slide. And if we approximate this formula by putting eta in place of this EC minus EF by kappa E minus EF by kappa T, then we can write that 1 by 2 root over of pi is the resultant formula, and n naught can be written as 2 into this one e to the power this, and this portion, this 2 pi m star kt by h square, can be written as NC. NC is called the effective density of states function in the conduction band. So this is the final formula, N naught. This is the final formula, N naught equals to NC. We have put NC here, e to the power EC minus EF by KT. So this is very important formula. Now we will do some problem on the basis of this formula. So NC is called the effective density of states in the conduction band. If we were to assume this, then at 300 degree Kelvin, we can put this value, that is Planck's constant, Boltzmann constant, the value of all these things we know. This is the general, we have calculated the this parameter, and the resultant answer is 2.5 into 10 to the power 19 per centimeter cube. That means carrier concentration in the conduction band. Similarly, for holes, we can conclude that if we put the limit, if we put, we can conclude that this density of states for holes is multiplied by probability distribution function of holes in the valence band, gives us the total number of holes in the valence band. So if we put here 1 minus Fe, and the resultant formula is like that. Fe, we know this Fermi-Dirac distribution function, this one, and 1 minus this one I have put, and after approximation, the formula is coming 1 minus Fe equals to exponential minus Ef minus E by kappa T. If we consider Ef minus Ev is very, very greater than 1, very, very greater than 80. Okay, so moving to our next slide. Similarly, we put the formula, that is density of states for holes, and the probability distribution function of Fermi level, that is Fermi distribution function, multiplied by the energy range. The dE is nothing but the energy range. We have concluded in our earlier slide that eta equals to EC E minus EC by KT, but for in the, that was for electrons. But in case of holes, we are considering as eta dash, that is ideality factor for holes, and this is the formula. If we put all these things here, the resultant formula is this. As in case of earlier slides, what we have done, that this section has been approximated as NC, but here as we are considering the holes now, this section can be approximated as NV, that is charge carrier concentration or hole concentration in the valence band. So the resultant formula comes here, P naught equals to NV e to the power minus of EF minus EV by KT. NV is called the effective density of states function in the valence band. So now, what is intrinsic carrier concentration? The use of Ni and Pi to denote electron and hole concentration in an intrinsic semiconductor. But for intrinsic semiconductor, since Ni equals to Pi, we usually use Ni to denote either the intrinsic electron or hole concentration. And if these two are equal, the Fermi level of an intrinsic semiconductor lies in between the forbidden energy gap, and this Fermi level then called intrinsic Fermi energy, EFI. So here we know the formula N naught equals to Nc exponential of Ec minus EFI, whereas for intrinsic semiconductor we are considering EFI by kappa T. But for intrinsic semiconductor there is no concept of majority charge carriers in conduction band that is equals to the electron present in the intrinsic semiconductor, that is Ni, and similarly there is no concept of hole present in the valence band. That's why that is equals to, that has been made equal to Pi, and that is intrinsic hole concentration. This is intrinsic electron concentration, and this is equals to Ni, because in intrinsic semiconductor P and N are equal number of quantity, and we put the formula Nv to the power minus of EFI minus EV by KT. So if we multiply these two, Ni into Ni, then we are getting Nc into Nv exponential. After subtraction, we are getting Ec minus EFI kappa T into exponential EFI minus EV by kappa T. Now, after subtraction of EFI, the resultant formula comes here, Ec minus EV by kappa T. So Ec minus EV we know is nothing but the forbidden energy gap. So NcNV e to the power minus Eg by kappa T. This is the resultant formula of intrinsic carrier concentration. Ni square equals to NcNV exponential minus Ec minus Ev by kappa T, or equals to NcNV e to the power minus Eg by kappa T. So this is the concentration, charge carrier concentration, electron concentration, hole concentration at 300 degree Kelvin for silicon, germanium, and also with compound semiconductor gallium arsenide. So moving to our next slide. Oh, obviously this is showing the intrinsic carrier concentration at 300 degree Kelvin of silicon, then germanium, this one, and gallium arsenide, this one. So we can see that germanium has much more intrinsic carrier concentration than silicon. So moving to our next slide, this is the charge carrier concentration. These are the formula, and if we plot it here, we can see that the graph looks like this. This is for germanium, this is for silicon, and this is for gallium arsenide. So moving to the next slide, the intrinsic Fermi level position. We can calculate the Fermi level position since the electron and hole concentration are equal for an intrinsic semiconductor. So we know N naught equals to Nc e to the power this minus Ec minus EFI by kappa T. And also as A and P equal in intrinsic semiconductor, that's why this is made, that equals to sign has been put here. So equals to P naught equals to Nv exponential of minus of EFI minus EV by kappa T. Now, if we subtract this from this, we are getting that minus EC plus EFI minus EV equals to kappa T natural logarithm NV minus NC. Now, EFI equals to half of EC minus EV, EC plus EV plus half of kappa T natural logarithm of NV by NC. This is very important formula to find out the intrinsic Fermi level position in a semiconductor. Now, if we can replace this NV and NC by the effective mass also, that has been shown here, and this EC plus EV has been replaced by E mid gap here. So if MP intrinsic hole effective mass of hole is greater than effective mass of electron, the intrinsic Fermi level will be slightly above the center, and if MP is less than Mn star, MP star, that is effective mass of hole is less than effective mass of electron, then the intrinsic Fermi level will be slightly below the center of the band gap. That means effective mass of holes higher signifies that there are a number of greater number of holes than the number of electrons. And this is showing that greater number of holes than the greater number of electrons. This is showing greater effective mass of holes is greater than effective mass of electrons. That means there are much more internal forces available in the valence band than in the conduction band. That's why it is critical to jump an electron from valence band to the conduction band. And the slightly above the center, Fermi energy level slightly above the center. So moving to our next slide, donor atoms and energy levels. As we know that the real power of semiconductor is realized by adding controlled amount of specific dopant. So this is the donor atom and energy level. This is Fermi energy level nearer to conduction band. This is the electrons elevated into the conduction band can move through the crystal to generate a current, while the positively charged phosphorus atoms are fixed in the crystal. If we see that phosphorus atom is added here, this is pentavalent impurity, group 5 element. 4 of the electron make the covalent bond with the neighboring silicon atom, but 1 electron is loosely bound in the phosphorus atom and moves into the crystal lattice. So in this way, number of electrons are increased in the semiconductor, then this becomes extrinsic semiconductor and valence band moves towards the conduction band. Similarly, acceptor atom, if we put boron in the silicon crystal, boron is group 3 element. This is acceptor atom because Not that this is accepting at this time, because it is ready to accept the electrons for possible cases. So that's why this is called acceptor atoms. And finally, the empty position associated with boron atom can be occupied and other valence electron positions become vacated. These other vacated electron positions can be thought of as holes. Here it is showing the valence band electron come closer to the Fermi level is closer to the valence band, and this is a p-type semiconductor. Next is ionization energy. What is ionization energy? We can calculate the approximate distance of donor electron from the donor impurity ion, and also the approximate energy required to elevate donor electron into the conduction band. This energy is referred to the ionization energy. That means the energy required to elevate donor electron from valence band to the conduction band. We can use Bohr model of the atom for the calculation. Generally, we calculate the ionization energy by mentioning this formula, by utilizing this formula, that is Coulomb force. This is the Coulomb force, and this is the centripetal force of orbital electron, that is mv square by r. So moving to our next slide, this is one example of group 3,5 semiconductor has been given, that is gallium arsenide. This is gallium is 3 and arsenic is arsenic 5. That's why this is becoming group 3,5 semiconductor, and it has it is providing a superior quality in many cases. We will study in later. Just I have mentioned what is group 3,5 semiconductor. Another name of this type of semiconductor is compound semiconductor. So equilibrium distribution of electrons and holes in extrinsic semiconductor. So adding donor or acceptor impurity atom to a semiconductor will change the distribution of electrons and holes in the material. Since the Fermi energy is related to the distribution function, the Fermi energy will change as dopant atoms are added. So EF is greater than E mid gap. Here we can see this was E mid gap. This is now EF is greater than E mid gap. So we can see that this section has been reduced. In case of, if you go to the earlier slide, you can see that in case of intrinsic semiconductor, this area and this area were same. These two areas were same because the electron concentration, hole concentration were same. But if we now consider the extrinsic semiconductor, we can see that as this is n-type semiconductor, the number of electron concentration is much more than number of hole concentration. So this region is become larger than this region. And the Fermi energy level has been shifted up. That's why the Fermi distribution function has also been shifted up. So this region is the hole concentration showing, and this region, this is for n-type semiconductor. Similarly, for p-type semiconductor, we can see that Fermi region has come closer to the valence band, and number of valence electrons is much more than the number of conduction band electron. That's why this region becomes smaller and this region becomes larger. So, and this is the formula as already mentioned in our earlier slide. So there are few examples based on the formula. So please go through it. NC given, NV given, Fermi energy level given, band gap energy of silicon is 1.12 electron volt. So this is the EC minus EF is given 0.25 electron volt, that is Fermi energy gap. But EF minus EV we have to calculate, that is 1.12 minus 0.25, that is 0.87 electron volt, because Rest of the energy obviously will be EF minus EV. So just put the formula NC 2.8 into 10 to the power 19 and exponential that this is Boltzmann constant and temperature and electron charge and also Fermi energy value. So if we put, we can calculate that carrier concentration in conduction band is this 1.8 into 10 to the power 15 per centimeter cube, and hole concentration in valence band is 2.6 into 10 to the power 4 per centimeter cube. So this is the comment that electron and hole concentrations change by order of magnitude from the intrinsic carrier concentration as the Fermi level changes by a few tenths of an electron volt. So moving to the next slide, we can derive another equation. This has already been mentioned in earlier slide. Again, detailed elaboration has been given here. Next is N naught P naught product. So N naught P naught product, just multiply N naught into P naught. So the right hand side is becoming NCNV e to the power this into e to the power this. So NCNV e to the power minus EG by KT, as it is becoming EC minus EV. The numerator EC minus EV is nothing but the energy band gap. So Ni square. So the product of N and P is always a constant for a given semiconductor material at a given temperature. It is one of the fundamental principles of semiconductor in thermal equilibrium, and it is N into P equals to Ni square. This is nothing but the mass action law. So Fermi-Dirac integral, we know the Fermi-Dirac function. It is already shown in earlier slide how it has come. Again, it is showing. Please go through it, you will understand. All these already been discussed in earlier slide. So next is, this is N dash, NF dash, whatever already been mentioned. Please go through it carefully. This is degenerate and non-degenerate semiconductor. So what is actually when discussing donor and acceptors, the concentration of dopant atom is assumed to be small compared to the density of host atoms. And there is no interaction between the dopant atoms, dopant electrons rather, in an N-type and P-type semiconductor respectively, if the number of impurities are less. This type of semiconductor is called non-degenerate semiconductor, that normal type of semiconductor. But if the impurity concentration is increased and the distance between impurity atoms decreases, the electrons from impurity atoms will begin to interact. And what is happening? The energy level goes up for N-type semiconductor and penetrate to the conduction band, and valence energy level, that is Fermi energy level, come to the valence band for P-type semiconductor. This is normal case, non-degenerate semiconductor, and this is degenerate semiconductor. Is there a higher number of impurities, more number of impurity atoms have been added. So EF lies inside the conduction band here in N-type semiconductor, and EF lies inside the valence band here for P-type semiconductor. This is called non-degenerate semiconductor. So when the concentration of X is, this type of semiconductor is called non-degenerate P-type semiconductor and degenerate P-type semiconductor and degenerate N-type semiconductor. So moving to our next slide, reading material, mainly Niemann. This is the book. If you have any query, please feel free to ask me at shunipa.roy@gnit.ac.in. Thank you very much for listening.